as Claudio said, I am going to present some of the works that I did during my PhD in France. And well, the title is just some of the main points that I will discuss in the presentation. So the context will be constellation of satellites, and then mathematical problems behind that will be unsplittable flows. And in the end, the last part will be a bit about theoretical stuff about decomposition methods. So a brief summary of the presentation. I'm going to start with the context of all this. So the beginning of the PhD, where I started, which is a big constellation of satellites that was ordered by a Canadian operator, which is called Telesat. Then after the context is presented, we will see that managing the internet throughput inside that constellation can be modeled with a flow problem, which is called the unsplittable flow. And I will talk a bit about how we solve that problem, and especially with randomized rounding. In the third part, I will talk to you about how to introduce the dynamicity of the problem inside of the dynamicity of the constellation inside of the mathematical problem, what it changes for solution methods and for modeling. And thus we will talk about the dynamic and splittable flows. And the last part will be a bit more about the theory and the algorithms. Initially, we wanted to improve the linear relaxation, which is a big part of randomized rounding algorithms that I will present in part 2. And to do that, a good way is to use decomposition methods. But in the end, what we did was proposed a new decomposition method that kinds of compete and does better for unsplittable flow problems in particular. So first, a little bit of context, a constellation of satellites. So the case study of my PhD was the Telesat constellation, which is a big constellation of telecommunication. So the goal of this constellation is to give internet throughput to users that are all over the world. But the goal is not to replace a terrestrial network. It's not to compete with it because it's completely unrealistic. The terrestrial networks is much faster, has much more capacity. Well, compared to the constellation, some kind of a god or something. And but the idea is to mainly support the terrestrial network where it is really complex to build, or where it is impossible, or way too costly. For example, in very sparsely populated areas such as deserts, well, it's very costly to build a network for only a few people. So maybe it's more efficient to give them internet access by constellation, who doesn't care about if you're well, where you are on the planet. Another application would be for the middle of the oceans. There might be boats or flights that might transit there, and they cannot access internet without satellites. So how does it work? The constellation is made of a fleet of satellites that orbit around the Earth, and we have a lot of users that are on Earth, and they want to communicate with some antenna relays that are directly connected to the terrestrial network. So they have a demand in megabyte per second for the internet throughput, and what they have access to is with their antenna, they are able to connect to the satellites, but also the satellites are connected to each other. And so the goal is to find a path from the users to the telecommunication relays, well, through the constellation, and give them access to the internet that way. So one of the first problems that you can encounter with this setup is actually the first connection to the satellites. It's a big problem on its own because there's a lot of possible satellites and visibility for each user usually. But what makes the problem really tricky is that you have both an irregular demand. So some parts of Earth will have a lot more demand than others. But in the meantime, when you have very densely populated area with a lot of demand, Then if you want to connect two users that are close to each other to the same satellite, the electromagnetic wave that you use to transmit the information might interfere. And so you want to both concentrate a lot of throughput where there is a high demand while managing the way you transmit that information through electromagnetic waves to make the connection as fast as possible. So this is not going to be the topic of the presentation. We are going to assume that this problem has been solved previously. So we consider that each user is connected to one satellite. Okay, so we will consider that the users are on the satellite. We will abstract the fact that they have their own antenna and that the problem of connecting them to the satellite is a big problem. We will consider that it's already solved. And once we do that, we can just focus on the satellites. And so we have a fleet of satellites for constellation. They are usually connected in some sort of grid. And so here I represent the arcs of the constellation. And so the goal is that we have some users that are on one satellite and want to communicate with another satellite, which is connected to their antenna relay. And we want to find a path inside of the constellation to send that throughput. Obviously, we have many users, so we want to connect all of them. And one of the restrictions is that each telecommunication link has not an infinite capacity. So we don't want too many users on the same link in order to be able to serve all the demand. And so we have to spread the demand over the constellation well enough so that everybody can be served. Another aspect which is really important for that problem, a question that you may ask is, do we really need only one path, or could we, for example, send the data of one user to several paths, split the information, and maybe that will enable more solutions that would make the problem easier to solve, to spread the demand. But unfortunately, that's not the case because, well, it's internet data, so the order is kind of important, the order in which it is sent and received. And if we use several paths, for example, if one of them is longer than the other, an internet packet that is sent first may happen to arrive before the one that is sent last. And in order to not have to do a reordering system at the arrival, it was decided to use only one path per user, which actually makes the problem much more difficult. Another thing that we have to take into account is that the satellites are orbiting the Earth. They are not geostationary. And so the users will not see the same satellites all the time. And so we have to update the path of a user when it changes its connection to a satellite, and the same for the antenna relays. When this change, we have to update the path of the corresponding user. So now that we have talked a bit about the context, how do we solve that with math? So we can, as you could have guessed, model the constellation with a graph where the satellites are going to be the nodes and the telecommunications in the arcs. And each user and its throughput is going to be a commodity which is to be transmitted between an origin and a destination. So the objective of the problem is to find one path per commodity inside the graph, and we want to spread out the demand over the graph. So we have capacities on the arcs, and we don't want to exceed that capacity. And if we overflow that capacity, we want to minimize the overflow that is created in the solution. So this problem is actually well known from the literature, and a common model for it is a classical flow formulation. It uses two types of variable. The first type is the FEK. Here is going to represent which arcs are going to be used in the path of the user K. And the second type of variables is the delta E, which will record the capacity overflow that is created on each arc. So for example, here we have too many people on the same arc, so we have an overflow of 3, for example. So the formulation, the mathematical formulation looks like this. We have 3 parts. First, we want to minimize the sum of the overflows, so it's the sum of the delta I variables. We have flow constraints. They ensure that the arcs that are selected for a commodity or for a user represent a path and not just random arcs that have no connection to each other. And the last type of constraint is the capacity constraints, which ensure that the flow of on an arc is lower than the capacity, or that any additional amount is recorded in the capacity overflows. So how do we solve this kind of problem? So first, we have to know that the unsplittable flow problem, actually, because we have only one path per user, is NP complete. So because the application we're interested in contains very large graph with several hundreds nodes, we don't want to find optimal solution. It would be unrealistic to search for optimal solution for this kind of problems. And so we were interested in heuristic and meta-heuristics. And one very good heuristic was proposed by Raghavan and Thompson, and is based on randomized rounding. And so the way we decided to approach this work was to propose an extension of that heuristic, which is called sequential randomized rounding, and that leads to better empirical results. So I will present those 2 methods quickly. Using this TOE example, we have only a very small graph with only one origin, one destination, and the only choice for the commodity is which arc they are going to use to go to one to the other. Okay. So what we said is that the problem is NP complete. So computing an unsplittable solution where the flow can only go on one of the 2 arcs is actually very hard to compute. But one thing which is much easier to compute is a splittable solution where you can split the demand and the flow of each commodity over the arcs. And it's actually the linear relaxation of the unsplittable flow. And this problem is actually just a standard multi-commodity flow. It's easy to compute because it is just a linear program, so we can just solve it as is with a commercial solver. Or there have been a lot of study for multi-commodity flows for the linear case. And we can use any of the algorithms that were specifically designed for that kind of problem. So the idea of randomized rounding is actually really simple. We start by computing a splittable solution, so solving the multi-commodity flow problem. And then we will kind of randomly round the flow of each commodity independently using randomized rounding. And so the idea in randomized rounding is that in the splittable solution, if, for example, if this commodity has sent 60% of its flow on one path and 40% on another path, we will put the flow of that commodity totally on the first pass with a 60% chance, and with 30% chance, we are going to put it on the second. So it's pretty simple. So it can lead to something like this. The problem with randomized rounding is that the commodities round their flow completely independently of each other. So they kind of not communicate. They don't communicate on which arc they are going to go in the end, and that can create a lot of overflow at some point. So the idea was to introduce a mechanism for them to not go on the same arc if it is going to create a lot of overflow. So how do we do that? The idea is to add just a little bit to the algorithm. So we start again by computing a splittable solution, and then for each commodity independently, we will choose a path for that commodity using randomized rounding. But after a path is chosen, then we will update the linear relaxation. So update the splittable solution that we used to make the next roundings. And another thing which is really important is that we will start by rounding the commodities with largest demand first. The idea is that you will round the commodity with largest demand while there is a lot of flexibility in the network, and then we will fill the gaps with the small commodities in the end. So just a brief animation of how it goes. So we will start with the largest commodity, so the one with the biggest demand, round it to one arc, for example, this one. And then we update the splittable solution so that the commodities that are using arcs that are overflown will try to move their flow to another arc, for example, this way. And then we will continue this process, by example, rounding this one, reorganizing the demands, and then rounding again until we reach a solution where everyone has been rounded. So we can see that in most of the time it creates better solutions. And in practice, we made a battery of tests on academic instances ranging from 30 to 200 nodes. And what we could see is that indeed the quality of the solution is much, much better. Usually the capacity overflow is divided by a factor of 5 or 20 or up to 20, which is a lot for that kind of problem. But in compensation, we have to increase the computation time because we have to solve several linear relaxation in a row instead of only one. This is usually not a problem because the Ragavan and Thompson heuristic was extremely fast. So increasing that computation time is much, much better than going for any kind of optimal solution. We also tested this algorithm on the Telesat instance, which was the case study of the PhD. It has a lot more nodes, a lot more arcs, which are the communication links, and a lot more users also. But actually, the fact that there is a lot more users make it, for some reason, much simpler to solve than the academic instances. And I will talk more about those results in the next part, where when I have introduced the dynamicity of the constellation. And the last thing I want to talk about in this part is we made also a theoretical analysis of the sequential randomized rounding. So the simple randomized rounding from Ragavan and Thompson has been, well, they proved an approximation factor for that algorithm, which is log m over log m over log log m. M is the number of arcs. That can seem a bit poor because it's not even a constant factor approximation, but actually it has been shown that it is the best approximation factor possible. So what we were able to do is to extend the proof extend their proof to the case where we update the linear relaxation during each step of the process. All this work led to a paper that was published last year in the Journal of Heuristics. So if you want more details or more insights, you can go check it out on their website. So next part of the presentation, I will talk about dynamic and splittable flows that try to take into account the fact that these satellites are orbiting the Earth. For now, we have only considered the static case where each person is connected to one satellite and try to solve this problem. So what are the new challenges? The constellation is constantly rotating, so we have a changing visibility over the satellites, both for the users and for the antenna relays. And so to solve that, we discretize time and introduce several time steps, and each time step is an unsplittable flow problem on its own. And among the time steps, there can be like users that change their attribution to a satellite, but also we could model that in another way, saying that we consider the antenna of a user and to which satellite it is connected. And so it can change the arcs that are possible to use in the network. So arcs may be added or deleted depending if satellites go in and out of visibility or just moved. Well, it depends on how we want to model that. So what is the objective of the dynamic unsplittable flow problem? We still have to find one path per commodity at each time step, and still have to minimize the capacity of the flow that we create. But we have another incentive, another objective. We want to minimize the number of path changes. Indeed, when a user changes its path inside the constellation, it kind of creates a disruption in its internet connection. And so for the quality of the service of the user, we want to minimize the number of times each user has its path changed. Unfortunately, some of the path changes are kind of mandatory. For example, if we have a solution for the first time step, because one user has moved its connection to another satellite because the old satellite was not in visibility anymore, well, we have to compute a new path, and it will create a path change and thus a disruption. But we cannot avoid that. The old path is not available. But once we try to recreate a new path, we may introduce some overflow on the arcs. And so if we want to prevent that overflow, a thing we can do is change the path of another user. But then we introduce that kind of balance between trying to minimize the overflow while not creating too many path changes. So the way we decided to balance those two objectives is to introduce some kind of a maneuver margin for the overflow. So some of the overflow is unpenalized. So you are allowed to create a little bit of overflow in the arc without getting any penalization. But after that amount, it will be heavily penalized. So the idea is to try to stay inside that margin, and inside that margin to minimize the number of path changes. So how do we solve the dynamic unsplittable flow problem? So actually the structure of the problem is very similar to the static case, even though the problem is much bigger because there is a time dimension. But we can still use randomized rounding to solve those instances, and still, since it worked really great on the static case, we decided to go for it on the dynamic case also. So we still compute a splittable solution of the problem, which is the linear relaxation still. And then we use randomized rounding to get the unsplittable solution. We created two types of methods, two types of solvers to solve that problem. Some solvers were only considering one time step at a time, so kind of in a rolling horizon procedure. So the idea is that we have the current time step, and we are given the paths that were used by each user on the previous time step. For those who have changed, we have no path to incentivize because the path change is kind of forced. But so we have this unsplittable flow problem where one path per user is kind of favored, and if you don't use it, you get a penalty. And the other kind of method that we went for was multi-time step methods that try to get all the time steps at once inside of the model. They are usually much heavier, but they can see farther in the future, so they can probably reach a much better solution if they were solved to optimality. We are not going to solve them to optimality, so we will see what kind of balance they introduce. So for the results of those methods, what we saw was that, so here the curves in red are for the multi-time step methods, and the blue one is one of the one-time step that we solved. What we saw is that when the multi-time step methods finished in the time limit that they were given, so here it did not finish, so we gave it bad results. We can see that usually they have a lower number of path changes, but they also have a higher computing time. That is to be expected because the model they try to solve through is much bigger, and they have a lot more variables to take care of at the same time. So they get better solution if you spend more time solving them. All this work and much more that I didn't get the time to present, especially about how to solve the multi-time step methods, which require a lot of column generation to solve the model, is presented in a paper which is currently in revision in computers and operation research. So a little bit about the application that I promised you a while ago. So we tried to solve the telestat instances with the dynamic problem. So the telestat instances contain 300 satellites and also 100 antenna relays that we take into account as nodes in the graph. And they have a little bit over 2,000 communication links that each have 10 gigabytes of throughput, well, gigabytes per second. We also have a very large amount of users. These users are already kind of aggregated, so it would be a much bigger amount, but we are allowed to aggregate them a bit. So only 30,000 users, which amounts for approximately 6 terabytes of throughputs that needs to be sent through the constellation. And as the time progresses, approximately 6% of the origin and destination of the users are changed at every time step because they change the visibility of their satellite. This is only a small amount because the time step or to simulate the constellation are pretty short, around 10 seconds. So what we could see for those kinds of instances is like surprisingly, having many users makes them actually easier to solve than having less users. Although it means more variables in the linear formulation, the fact that we have many users means that the unsplittable solution is not that far from the best splittable solution. Each user only has a small demand, so rounding it does not make a big change. So we don't have big updates to make every time. And it makes the solution work very well for these kind of instances. And so for practical results, we could see that by only allowing 2% of the demand to overflow the capacity, so that's the margin we gave to the solver, we would need only 10% of additional price changes. Additional are the ones that are not forced upon us by the change in visibility. So with 10% additional path changes, we can reduce almost all overflow on the arcs. One thing that we could need to improve still is the computation time. For now, it's 100 seconds per time steps, which is a bit too much for that kind of application because the time steps are usually 10 seconds. But since my code is mainly Python, I'm pretty sure that this can be improved drastically by just changing the programming language. And also trying to solve the linear relaxation in a better way. But that's for another work. And one thing that we could see also is that actually we don't have any incentive in the problem to look for short paths. But it kind of helps to still give that incentive to the solver, because otherwise it will use unnecessarily long paths, and this might end up in the end creating more of a flow through the randomized rounding process. And so actually putting a small penalization to each arc or to the length of the path used in the linear relaxation actually helps the algorithm both go faster and find better solutions. So sometimes just a 10 to the -5 penalization to get short paths is very helpful. So last part of the presentation, completely different. We are going to talk about decomposition methods. That's the last work of my PhD. So we go back to our static unsplittable flow model. So the thing I want to highlight is only that we have, an objective, but also only two types of constraints, the flow and the capacity constraints. And this model is a mixed integer linear program. And so I will visualize it with that kind of model to explain how the decomposition method works. So because it's a linear program, each type of constraint introduces a polyhedron that we want to search our solution inside. And also the objective is just a direction in which we want to go as far as possible. So the best solution would be the furthest in that optimization direction that is inside the intersection of both polyhedrons, because they want to satisfy both types of constraints. It's all, some of the variables are integer. The flow variables are integer because it models the fact that there is only one path per user. And so only a discrete sets of solution inside that space is allowed. And in randomized rounding, we had this idea to use the information from the linear relaxation to build the integer solution, which is the unsplittable solution. And it kind of makes sense because usually the intersection of the two polyhedra are a pretty good approximation of the real solution space that we want to look into. However, it's a good approximation, but we might want a better one. And we were thinking that maybe if we get a better approximation and a better linear relaxation, then the solution that we get after randomized rounding could have also better properties or just better solution quality. And so one idea we can try to get a better approximation is to see that the polyhedron modeling the capacity constraints is not fitting properly the integer points that it contains. And so we would like to replace this polyhedron by well, the convex envelope of the integer points that are inside of that polyhedron. This would make shrink the capacity constraint polyhedron, and this would also make the approximation of our solution space much better. It might not be optimal, but it would still be much better in most cases. However, one problem with going for this approach is that although we had the capacity constraints given as a small set of linear constraints in our model, there is no way to model, well, at least linearly in a compact form, the convex envelope of such polyhedron, well, of such points. And so we can only know this polyhedron kind of implicitly through an optimization oracle. And we cannot directly solve, we cannot find the solution which is farthest in the optimization direction inside the intersection of our flow polyhedron and our new smaller polyhedron. We cannot do that directly. So what we need to do is to compute an approximation of this implicitly known polyhedron. And to do that, a very convenient method that was created is the decomposition method. So I will talk about two classical decomposition methods, and then I will present a new decomposition method that we proposed that actually have really good results for the unsplittable flow problem, especially. So the first one I will talk about is the classical Dantzig-Wolfe decomposition. And the idea in the Dantzig-Wolfe decomposition is to try to grow an inner approximation of the polyhedron we want to approximate. And on the other hand, we have the Fenchel decomposition, which is much less known. Probably maybe 1 or 2 person max knows it in that room, I would guess. And the idea is that it will try to compute an outer approximation of the polyhedron. Yeah, so those two decompositions are kind of dual to each other. So I will present them very briefly. So first, the Dantzig-Wolfe decomposition. How does it work? So the idea is that if we have some of the integer points inside our polyhedron, we know that we can optimize over the convex envelope of those polyhedrons. And so this can make our first, if we have some of them at the beginning, we have a first approximation of our polyhedron just by optimizing over the convex envelope of this small set of points. So the first thing is to solve over that approximation intersected with the flow polyhedron and find the optimal solution. And then the dual variables of the linear program that we solve in that case will give us a direction in which if we find a point inside of our polyhedron, which is far in that direction, it may help us improve the solution that we got. The yellow star that we have may improve in quality if we find a new point. So if we get the farthest point in that direction, we can add it to our approximation, and this will, in that case, indeed increase the quality of our solution. And we can continue by following the direction given by the dual variables until the solution that we find, we can prove that is the optimal one. So that's the idea for Dantzig-Wolfe decomposition. And the Fenchel decomposition is kind of the other way around. We start with an outer approximation of the polyhedron. So usually it's just well, in our case, it's just the capacity constraint that were given at the beginning. And we will optimize over, so here is just optimizing over the linear relaxation of the problem, the first one. And then what we will do is we will try to separate that solution from the polyhedron we try to approximate by finding a cut. And then we will add this cut as a constraint to our linear relaxation to increase its strength. And we will continue finding cuts until we can show that the solution that we get in our master problem is indeed optimal. For example, because we cannot find a cut that separates it from the polyhedron. Okay, so that's the main idea. A thing that I did not tell you is how do we choose the cut well, at least which cut are we going to add to the polyhedron? Because there is plenty of cuts that would separate one point from a polyhedron. So which one are we going to choose? And actually, what we can do is that in the separation problem, we can add a normalization of the coefficient of the cut we want to look for. And this normalization will entirely determine the cut that is returned by the separation problem. So I'm going to talk about two types of normalization that will help for the rest of the presentation. The first one, if we force the coefficient to have a small norm in L2 norm, then the cut that is returned by the separation problem is the cut that goes farthest from the point we want to separate. So it makes for a good normalization because usually the cut that is returned is kind of deep in a certain sense. But one of its main drawbacks is that sometimes it does not return a facet of the polyhedron. So we may end up adding cuts that are not necessary for the description of the polyhedron in the end. So we may lose some time on that. Another normalization which is possible is the directional normalization. And so the cut that is returned in the directional normalization is simply the cut that intersect so we have, for the directional normalization, we have a point inside of the polyhedron. And the cut that is returned is simply the cut that intersect the segment which is connecting the point we want to separate to the inner point that we have. And actually, one of the good properties of that normalization is that it always returns a facet of the polyhedron. So in that sense, it has a very good property. But we still need to have a point inside of the polyhedron to make it work. So first, before presenting the new decomposition method, I will show a bit some results that we had on the unsplittable flow problems. So here the black curves is for the Dantzig-Wolfe decomposition, and the Fenchel decomposition is in blue. So the axis is the computing time. So through the iteration and as the time progresses, the two decomposition will find bounds on the value of the optimal solution. And when those two bounds connect, we can show that the solution is optimal, or if they are close enough to zero, if the difference is close enough to zero, we can stop the process. And so what we can see is that the Dantzig-Wolfe decomposition has kind of a slow start, and we think it's due to the degeneracy of the master program. but in the end, it kind of converges pretty fast. And it's kind of the opposite around for Fenchel decomposition. It has a really good start, but in the end, it kind of slows down very quickly and kind of never converges. Well, not in any reasonable computation time. So that's why we try to find something better and more appropriate. And actually, what we ended up to was some kind of some sort of hybrid of the two methods, using ideas from both methods to make them more efficient. So an important fact to understand what's going on in our lecture is to know that in the separation problem, the primal variables that we get out of the separation problem in the Fenchel decomposition is the coefficient of a cut that will separate the point we want to separate and the polyhedron we want to approximate. But actually, the dual variables are going to be vertices of the polyhedron that satisfy this cut to equality. So if we check for the dual and the primal variables, we get two types of objects that we can both use and use that information. And the idea is that we are going to have both an inner and an outer approximation of our polyhedron, and we are going to add the cuts to the outer approximation and the vertices to the inner approximation, to one to shrink it and the other one to grow it. So how does it work? We'll start with the two approximation, and so one outer and one inner, and so two master programs. One which is just the Dantzig-Wolfe master program, and the other one is initially the linear relaxation. And we will solve over both of them to get two solutions. And once we have that, we can ask the solution. We can consider the following question. So we have those two solutions, and they kind of seem to disagree with each other on where is the actual border of the polyhedron we want to approximate along the segment that connects them both. One of them says it's more around here, and the other one says it's here. And what we can try to find is actually where is this border of the polyhedron along that segment. And so this is exactly the separation problem for the Fenchel decomposition. We can find that border along that segment by using a directional normalization with the inner point being the solution from the Dantzig-Wolfe master program that we just computed. And so we get a cut that we can add to our Fenchel master program and some vertices that we can add to the Dantzig-Wolfe master program. And then we can continue until the two linear relaxation, well, when the two approximation agree on the position or at least on the value of the optimal solution, we can stop the process and say that we have a good enough solution. Okay, so once we had done that, we also realized that sometimes the separation problem with the directional normalization had some instability issues. And so we also proposed a new method to solve the separation problem. And the idea is to go for an iterative approach. And at each step, we're going to solve a separation program, but not using the directional normalization. We try to use a normalization that does not have any numerical instabilities. And so we compute the cut that would be returned by the directional normalization, but without going through all these numerical instabilities. So we start with our separation problem with one point inside and one point that we want to separate. And the idea is to compute the cut that would be associated with any other normalization. So here for the presentation, I will use the norm 2 normalization. So we find that cut. And what we can realize is that finding the cut for the directional normalization, which would be this facet of the polyhedron, is the same as finding the cut for this point to separate along that segment. If we stay along the segment, the resulting cut will be the same. So we can move the point and project it along the segment toward the cut that we just created. And then we continue this process by solving again the separation problem with the L2 norm and projecting until we reach the border of the polyhedron we want to approximate, and then the last cut that we created is actually the one we want to return. So that was really good. It worked great for solving the numerical instabilities. And so we had the following numerical results. So here I did two curves. The yellow one is the Dantzig-Wolfe-Fenchel decomposition, which is the one that we proposed. And the red is the same, but with the iterative approach. So what we can see is that when the red approach works well, when it does not encounter numerical instabilities, it's not always the case, then the iterative method is a bit slower because it has to go through this iterative process to solve the separation problem. But sometimes, because of the numerical instabilities, the separation problem would never finish, and then the yellow method would kind of stop back here and never reach its goal. So what we can see is that the method that we propose kind of combines the advantages of both decomposition before. So it actually has the same great start as the Fenchel decomposition, but without the slowing down effect. So it has a very good convergence for a lot of instances. And in some other instances where there is less users in our unsplittable flow problem, the Dantzig-Wolfe decomposition in that case is more competitive because with less users comes less degeneracy of the master program. And so in that case, we can see that well, both methods are kind of similar. The Dantzig-Wolfe-Fenchel starts better, but then it kind of get beaten in the end, just at the last point of convergence by the Dantzig-Wolfe method. And so what we think is that our method can work really great on cases where the Dantzig-Wolfe method really has trouble solving, which is the case where the Dantzig-Wolfe master program is really degenerated. And why we think it works really great is because we don't actually use any dual information. Like in the Dantzig-Wolfe decomposition, we use the dual information of the master program to get that direction in which we want to get a new point. And the degeneracy is basically saying that this information is not good at all. And so our method does not suffer from degeneracy because it does not use that dual information to make its computation. So in cases where there is no degeneracy, I think that the Dantzig-Wolfe method would go faster. But when, well, there is a lot of problems that are known to really not work well with the Dantzig-Wolfe approach. And in those cases, I think that our method could make a good progress. And that's just a slide to saying that sometimes the iterative method, the non-iterative method doesn't work. And so all this work on the decomposition methods is also where we are going to try to publish it in a paper. For now, we only have a preliminary technical report, but I wish to try to send it to a journal as soon as possible. So as a conclusion, we saw that there is a big need for a better algorithm for for constellation of satellites, because for now, managing the throughput of the internet throughput of the users inside those constellation is still a big challenge. And we can model that with static or dynamic unsplittable flows. We improved the randomized rounding for solving those problems and got very nice results on our practical application. But also we were able to extend the theoretical guarantees of the randomized rounding algorithm to the sequential randomized rounding. And finally, we looked into decomposition methods initially to get our randomized rounding algorithm to work better, but in the end, just to work on the theory. And we ended up with a new algorithm to solve, to do the same thing as the decomposition methods, And the practical results were very good on the unsplittable flow problem. For future work, maybe we will try to, so we left behind the problem of choosing to which satellite each user is connected. And so maybe we could try to integrate both the dynamic unsplittable flow problem with that first link problem. Another thing that that still needs to be addressed is any random phenomenon, such as weather that disrupts the quality of this first link, but also failures on the satellites or on the antennas that would prevent any connection. So try to take those into account. For sequential randomized rounding, for now, it is a greedy heuristic. So any rounding that is done is fixed until the end of the algorithm, but we could try to introduce backtracking. So trying to change the path of a fixed commodity if we think that it would be better later in the algorithm. And also trying the sequential randomized rounding on other problems. It might work very well on packing and covering problem because they have the same structure as the unsplittable flow problem. And finally, for the decomposition methods, there is a lot of work still to do, especially on the topic of normalizations. So we proposed this, well, we didn't propose actually those normalization, but addressing the question of what is the best normalization to use in which case is still a completely open topic. We could also try to extend the ideas that we talked about for the Bender's decomposition, which has which is very, very similar to the Fenchel decomposition. So trying to add the idea of normalization and internal approximation to the Bender's decomposition would also probably lead to improvements in those domains. And finally, we made experimental results only, well, for the decomposition methods only for the unsplittable flow problem. And it might be interesting to see if it actually works well in other problems where the Dantzig-Wolfe master problem is known to be degenerate. And so we could try other types of application for those methods. I think that's all. Thank you for your attention, and I will answer all your questions.